Hi everyone. So I have decided to go with the topic Schrodinger equations for this lecture. Schrodinger equation is very important in quantum mechanics, and largely I can safely say that this quantum mechanics largely revolves around this Schrodinger equation. And the equation that looks very fancy, but in the realistic terms, if you see that there are a lot of constants involved, like I, h cross, and then we have mass also. So lastly, what happens here is that any information that we need to get from the system, quantum system, it just revolves around this very parameter. That's what we call as psi, and this is what we call as wave function. Okay, so a little of motivation as to why we need quantum mechanics at the first place, and yeah, largely why do we need Schrodinger's equations at large, is from a fact that if we look at a classical system, say for example, I have a ball, and this ball is thrown up with some force. In a classical system, and this ball, we conceive it as a particle and use the relevant Newton's equations to get the information from the system, like when the particle will reach to any particular point, or what would be the position of a particle at particular time. So these all kind of information we can deduce from the system, and I mean you can get a position using this equation, knowing that you have an acceleration given. And similarly, you can also find, say, momentum, p equals to dt. Similarly, velocity of this object when it's thrown up at any point, at any position, you can get the velocity using the relevant formulas. Okay, and these you can deduce from the one major formula only. So whole of the dynamics of this whole system revolves around the Newton's equations, which are very straightforward and do not involve a lot of ambiguity. Rather, these are very pinpoint correct to the given parameters. Like if you know the mass, already you must be knowing the mass of a particle, and if you know the acceleration, you'll get to know about the force. And I mean, then if you know about the force and you know what is the mass, you can also get the acceleration. So very straightforward calculations are involved. Even for the energy, for example, you can get the kinetic energy as 1 by 2 mv square. So this is what the all information we can get for a classical system. Now, if we just turn around and see that what was the need for a quantum system to be involved, and why do we use the Schrodinger equation at the first place? So the thing that Schrodinger equations involve the wave function is for the fact that in quantum realm we don't see particles. I mean the object as a particles, rather we conceive them as waves. So if we just have an analogy of this very object in the quantum system, you will have a wave actually instead of a, say, a particle. And when it evolves in time, it will again be a wave, okay, of any pattern that you may say. So this is conceived to be a wave from one position to other position. And for a wave, and there is no certain position for a, I mean you don't have a very particular position, rather you deal with the probabilities. And that to say that in a waveform we just use a term called as amplitude to signify where exactly the particle could be, or where exactly the atomic or the quantum realm particles would be, for example electrons. And because the waves are associated, so is the equation. We cannot use the regular Newton's equation for getting the important parameters like momentum or position. And that is why we are using what we call as a Schrodinger's equation, where this psi is simply the wave function, which gives us an idea that where exactly, not exactly where the particle, where the probability of a particle is most likely to be. So yeah, so this is about the wave function. And if we just look at these function, I mean the Schrodinger equation, this is an equivalent to an equation in the classical mechanics as well. So we have this equation, that is total energy equals to kinetic energy plus potential energy. Similar kind of this equation is also same. So here one this I h cross d psi by dt is our total energy, where this very term would be the kinetic energy, and this one is potential energy. So uh, actually this is constrained given the fact that we when a wave actually wave would evolve in time, it won't be evolving any random direction. Rather, this would be constrained by these energy equations, which will say that these energies are constrained, and so we'll have the energy levels for a particle to move in. So it will be a constrained motion, and it won't be a random sort of a motion. Okay, so yeah, let me get some more space here. Okay, so one of the important things about the Schrodinger equation is, let's say we have a particle actually in a box, and there is an ambiguity. See, in a classical system, we know a particle is at any position. So, for example, it's in this position or in that position. We are very sure about it. But since in quantum mechanics, this approach is sort of taken by the wave approach, and associated with any particle will have a wave. So, for example, this is a wave of an electron, finding an electron. So, you are not sure about where exactly the electron would be. It could be anywhere between this position to this position. Say x equals to x naught to x equals to uh, xt. So, it could be anywhere here, but the probability would be highest at this very point. So, for example, if I take a box, this box is very constrained. Let me take a bigger one. So if I have a box and I say that I just put in a particle in this very box, and then I just want to see that where exactly this box is, where exactly the particle is. So given that this box is closed, so the position of the electron, if I say, or a particle, quantum particle, would be a superimposition of all these points. So there's a possibility it could be at any point. It could be here also, it could be here also. So that is what we call as a superposition, that it could be in a superposition of all these points. So that is really one of the concepts that is also related to Schrodinger's cat that we say, a very famous actually sort of related example to say that if cat is alive or dead if it's in a box with poison in it. So until and unless you don't put, I mean, you don't see the actual where exactly the cat is, you are just saying that it is in a superposition of either alive or dead, and that, in other words, could say that it's alive as well as dead. So I mean, the related concept is quite familiar, that because it could be at any other point. I mean, the position of an quantum object could be at any point. You don't know till you measure it. So it would be in a superposition of all these points. But once you open the box and you see the particle at any position, say this position, all other superimpositions do crash out, and you just have a exact point. Okay, there's no further ambiguity in it. Okay, so this is about a particle in a box. Actually, this is very important in quantum mechanics to get an idea about what I mean, the motion of the particle would be. Uh, Okay. I guess that's it from my side because I've already covered a lot of, I've run over time. So that's it from mine for this lecture. Thanks a lot.